Hello, I'm Dylan Randall. I'm a professor in water quality engineering at the University of Cape Town in South Africa, and I'm also a co-founder of a deep tech startup called PeeCycling. Today I want to talk to you about how we've developed circular sanitation by engineering novel urine recycling systems. The humble toilet. I'm sure you have used one already today, but there are billions of people who don't have this luxury. How many of us have considered the amount of drinking water we waste every time we use it? Or what happens to the waste when we flush? Or what's in the waste? Take this for example. Urine only makes up 1% of the volume of this waste stream, yet it contains over 80% of the nutrients we flush away. Furthermore, 80% of global wastewater is not treated or reused, and we have unpredictable water scarcity and availability because of climate change. In addition, 2.4 billion people lack access to proper sanitation, the basic toilet you and I take for granted. And we have soaring fertilizer prices and limited phosphate rock reserves. These are all global, interconnected challenges, and they can be partially solved by focusing on our urine, the liquid gold of wastewater. The potential to replace synthetic nitrogen from human urine is significant, especially in Africa. But before we go further, let's understand some very basic urine chemistry. First, about 90% of the nitrogen in urine is fixed as urea. This urea decomposes in the presence of an enzyme called urease and produces CO2, ammonia, or ammonium. This brings me to the first problem, nitrogen loss. So if we look at preventing this from happening, we have to stop the urease. And we can do this by lowering the pH or increasing the pH. So the urea stability at various pH values is important. For example, if we just have fresh urine and we leave it, we see that the total ammonia concentration increases. And if we have total ammonia with some urease present, the amount formed rapidly increases in a very short space of time. This is because this reaction is happening. However, if we take fresh urine, add calcium hydroxide and urease, we see that the total ammonia stays constant. In fact, it's not so much the calcium hydroxide, but the pH of the solution that prevents this from happening, and that's the key. So the critical pH for preventing urea hydrolysis is governed by the pH of the solution, as this graph shows. So what we find is that when we operate at a very high pH, above 11, we stop the reaction from occurring and we get no ammonium forming. The pH of fresh urine should therefore be kept higher than 11. The saturation of calcium hydroxide in urine and water, what we also see is that it gives us a similar pH at saturation for different temperatures. So what would happen if we use different urines? So what this graph shows is that for each different colored curve is a different urine composition. And we see that the amount needed to create a saturated solution varies. As a result, we recommend a dosage of 10 grams per liter of urine. So when you dose with calcium hydroxide, the amount of calcium hydroxide dissolving depends on the composition, and the saturation pH is fixed at a specific temperature. This allowed us to develop a design chart of sorts, and it gives us the ideal operating region defined by the thick black curve. So essentially, at about 25 degrees, you want a really high pH of 12.5 or above to ensure that you are above this threshold. The second problem is, how do you effectively collect urine? So you could use what is called a no-mix toilet, and like the name suggests, it doesn't mix the feces and the urine. There's also the Laufen Save toilet. This is what it looks like from the top. It looks like a normal toilet, but from the side, it cleverly allows urine to be separated through a two-pipe system within the toilet and effectively separates it from the feces. Or you could collect it directly from urinals. How do you prevent nitrogen loss and collect urine? So to cover this, we developed a very simple fertilizer-producing urinal as shown. It consists of a removable collection container, a funnel, and a splashback for obvious reasons, into which you would add calcium hydroxide. And then you simply add urine. It is essentially a passive dosing system because the container to which you add the calcium hydroxide and urine, the calcium hydroxide dissolves. You add a little more urine and a little more dissolves, and so on. Provided you have enough calcium hydroxide, you would have a high pH and you would stop the reaction from occurring. So this allowed us to collect urine while also retaining nitrogen, but it also results in the precipitation of phosphorus because of the high pH. We developed a second generation that cleverly allows the user to mix the contents of the urine. And it essentially works by a foot pedal with a linking rod and a lever that oscillates springs under slight compression and creates an up-down motion that essentially mixes the contents every time someone steps on the lever. We are now developing a third generation of these urinals in collaboration with a UK-based urinal company called Whiffaway. The third problem is how to remove water using an energy-efficient method, because urine is about 95% water. We use reverse osmosis to remove water. So conceptually, you have 1,000 liters of urine with a 70% water recovery. You get 700 liters of water and 300 liters of a liquid fertilizer and no waste stream. So why reverse osmosis? Well, it is an established technology, it's commercially scalable, and it uses substantially less energy than other methods. As a comparison, if we compare the energy required for reverse osmosis, eutectic freeze crystallization, nitrification, distillation, and evaporation, we see that it's substantially less on a kilowatt hour per meter cube basis. If we change the units on the y-axis to a kilowatt hour per kg nitrogen basis, we see that it's even less. This brings me to the fourth problem, membrane scaling. So because we have a saturated calcium hydroxide solution, because we added it to increase the pH, essentially what it means is that when we concentrate this, we would very likely form a solid. So this amount dissolves, and then this amount has the potential to form a solid. The reason this happens is because of CO2 dissolution and calcium carbonate precipitation. So as air blows over the system, you have an exchange of carbonate ions forms with the calcium to form calcium carbonate. And as a function of pH, because we're at a really high pH, you can see that we have predominantly more carbonate ions than bicarbonate ions. This resulted in a development of an integrated urine treatment process, where we stabilize the urine with calcium hydroxide. We then filter out the calcium phosphate. We then bubble air through the system to force it to form calcium carbonate. And hence, we concentrated using reverse osmosis. We tested this at lab scale, and these are the results obtained. This is the small little unit, and this is what it looks like inside. Essentially, that's the membrane sheet. We have a 70% water removal, 100% phosphorus recovery, and an 80% nitrogen recovery, and about 97% potassium recovery. So why not try acidified urine in the RO? So we did, and if you remember this equation, you see that acidified urine should also work because of the low pH. But when we tried it, we formed these little crystals. And guess what they are? They are kidney stones, uric acid dihydrate, and they would scale the membrane. So we didn't investigate this further. We then moved to a full-scale urine treatment plant. It has a design capacity of 3,200 liters per day. It has a 69% water removal and very similar nutrient recovery. We have a very low energy recovery of 9 kilowatt hours per 1,000 liters of urine that we treat. So just some urine economics. If we collect just 1,000 liters of urine per day, we'll save approximately 2,000 liters of water. We would produce 600 to 700 liters of water that could be reused, and we would reduce energy and infrastructure burden by about 13.5 tons of CO2 per year. From this work, we also launched PeeCycling, and this is just a picture of the team. We have also been shortlisted for the Royal Academy of Engineering Africa Prize in Engineering, and the winners will be announced in October. We have also partnered with Bidvest to look at urine collection at the DHL Stadium in Cape Town. This is what the urinal trough looks like at the stadium. And as a result, we retrofitted the plumbing system to install a collection tank. On the 25th of April, PeeCycling collected its first batch of urine from the Cape Town Stadium. And this just shows you the sheer amount that was being collected even before half-time. In total, we collected 2,700 liters of urine from one of 4 bathrooms and only urinals, and the stadium had about half the capacity, so the potential is substantial. So our vision is to scale this engine across Africa and the globe, permanently turning a liability into a sustainable, high-margin, circular sanitation industry. Thank you.